Very well. So let's now go to problem number 1. Problem number 1 is 26.4. It's a silver wire. And you're being asked what is the current through the wire. Well, the current through the wire is the charge through the wire divided by the time that it takes for that charge to flow. You know the charge is given, you know the time is given, so clearly you can calculate the current. The current density J is that current divided by the cross-sectional area. The cross-sectional area, which in the case of the silver thread, silver wire, is just the pi r squared of the cross-section. But if you look in section 26.7, where the idea of drift velocities are discussed, you will see that it's also equal to n, which is the number of free electrons per cubic meter in a metal. Q is the charge of the electron times that drift velocity, average drift velocity I should say, and if you want to be really cute, complete should say, there has to be here a vector, and there has to be a vector here. So since you know the number of free charges per cubic meter, you know the charge of an electron, you know J because you just calculated I, and so obviously you will find the drift velocity. And that drift velocity is of the order of microns per second, which is exceedingly low. I mean, it is so low that you cannot even imagine that these electrons would drift so slowly. And this comes down to a major misconception that most physicists have. Most physicists think that the energy that is transported by the silver wire in this case is in the form of kinetic energy of the electrons, but that's not the case. If I would here have this silver wire and a certain current I would come in, and I had here a resistor, and say the resistor R was something like 100 ohms, then we both know, or should know, that the power dissipated by this resistor equals I squared R. And the energy dissipated is the power times the time that you let the energy come out every second. Now, the drift velocity, as you will see, can be made arbitrarily small by making that cross-sectional area of the wire very, very, very large. You will see that immediately, because notice that if you make this cross-sectional area very large and you keep the current the same, then J would come down. So the drift velocity will come down. And so you can come down to a negligibly small drift velocity. And if the energy that is going into this resistor R, if that were really the sum of all the kinetic energies of the electrons with a mean drift velocity Vd, if it was the sum of all these electrons, then obviously that cannot be, because this drift velocity we can make arbitrarily small, whereas this number is not changing. It's independent of this drift velocity. So this is a very difficult concept, and I want you to think about that. It's not so obvious, and to be frank with you, it's not not something you can easily see. But what I want you to remember is that the energy that is transported through a wire to a resistor, and the energy comes out there in the form of heat, that energy is not going through the wire in terms of kinetic energy of the electrons.